Recording in progress.
Yeah, comes on everyone. Let's start off. Hope everyone has gone through the problems. We have done almost 72 problems so far. Perfect. Let's go ahead. Let's start with the problem. This is the top view. We have a spring here. This point O is fixed, so one end of the spring is fixed. K is the spring constant, L is the natural length. On the other side, we have a particle of mass M. Now, remember, this entire thing is on a smooth floor, so there is no gravity. And this thing is given velocity v at an angle theta like this. What do you think will happen? So when you give it like this, after some time, the spring will stretch. Two things will happen, isn't it? The spring will try to rotate, the spring will try to stretch, and then it will keep going like this. Can you see how it is going? It is trying to go in a circle, but the radius is increasing. And then again, the radius will start decreasing. Then the spring will compress. Then the spring will again elongate. You're getting it? The motion will be quite weird. It won't be a circular path. Find the maximum elongation. One end of a spring is fixed to the ground. The other end has a mass m. Just get me the equation. Solving, there are too many variables, which is given speed u at an angle theta. Find max elongation. I told you this thing multiple times. When you see a question, what is the first thing you should see? Okay, what do I need to use? Like, remember the entire algorithm I taught you once. Now, what did I ask you? Maximum elongation. It's clear. I can either use force and torque method or I can use a conservation. And I told you the keywords also. If you just want to study about something in the final situation, final speed, final position, final elongation, it's conservation. Make sense? So there, clear we have to use conservations. And there are three conservations we have. First is linear momentum. Second is energy. Third is angular momentum. Now you need to ask yourself, which one can I use? That is how, your thought process will go into your mind. Now, first thing you ask yourself, can I conserve linear momentum? Can I conserve linear momentum? Yes or no? Can I conserve linear momentum? Yes or no? See, understand what I'm trying to teach you now is that only. This is what will go through your head. This is actually what should go through your head. It might be like 10 times faster. Now, because I'm telling you step by step, it might look slow. And this is what people call, instinct. When you have done the problem with so many steps, right? You skip the steps and you actually solve it multiple times. First thing, if you see, to conserve momentum, what should be there? F external is 0. Now, in my system here, spring and the particle, are there any external forces? There are. The point O is fixed, means someone is holding it, isn't it? Since O is fixed, there is an external force, a ground or something is holding it, or else it will move. F external is not a 0. Therefore, momentum is not gone. So one conservation is gone. Second conservation, energy. To conserve energy, what should be there? Work done by external must be 0. But there is an external force, but there is no displacement. You're getting it? On point O, there is a force, but there is no displacement. Again, same thing. Since displacement of O is 0, work done by external force is 0. Therefore, energy is conserved. Again, remember the definition of work: force into displacement of point of application of force. This is what should go through your head when you do questions like, okay, this I can do. Next thing, if you look at the spring force, it is always passing through O, angular momentum. If the spring force is passing through O, therefore torque about O is 0, implies angular momentum about O is constant. So angular momentum also can be conserved. Making sense? So there, I can conserve energy, I can conserve angular momentum. Two conservations will work. So when you do conservations, what is the first step you need to do? Draw your final diagram. Making sense? When you use force and torques, the first step is draw an FBT. When you use conservation, the first step is final diagram. Again, I'm telling you, in physics, if you don't know how the final situation looks like, you will have a problem. You can't solve 90% of the problems. The biggest problem is not your concepts. Most of you can't visualize. You should take your time. It's okay. When you're solving a question for 6-7 minutes, it is fine if you sit for 3-4 minutes and only thinking about the final situation. Okay, in this will happen. That's why it will look like this. Maybe it will be like this. That's a very important part. That's what will actually make your physics stronger. Most people think they just blindly solve the questions without an understanding what is happening, why it is happening. So don't do that. That way, right? Physics may never gain confidence. When you're seeing a question, you should really know what is happening. Now, how will the final diagram look like? This thing must have gone little front. The spring must have become like this. This must be L plus X, where X is the maximum elongation. Again, don't expect suddenly you will know the full answer. Start. Getting it? If there are 10 steps to reach the answer, start with the first step. Slowly, it will be a struggle. So don't be misguided. Life is not so easy. It will take time. You have to think, you have to figure it out. Now we have 3 options. 4 options actually. Do you think this will be at rest? At maximum elongation, do you think it will be at rest? That is how you should think, right? Maximum elongation, the rest में आएगा क्या? Maybe, may not be, right? So the thing is, you don't know for sure. Make sense? You're getting, this is what I think. I'm teaching you my thought process. Because generally I feel, elongation matlab maybe V0 हो सकता है. But are you 100% sure? I'm not 100% sure. So that option is maybe. That is not for sure. ठीक है. Can the velocity be like this? If the velocity is like this, then this V cos alpha will stretch the spring, isn't it? That means this is not maximum elongation. ठीक है. Can V be like this? Then V cos alpha will compress the spring. That means this is not the maximum elongation. Making sense? That means if V has to exist, there is only one possibility. It has to be perpendicular. Is that making sense? Whenever there is a maximum elongation or compression, the velocity of the particle Maybe zero, I don't know that. But if there is a velocity, it has to be perpendicular. We will prove it is not zero. Angular momentum won't be conserved. At max elongation or compression, the component of velocity along the spring must be zero because it's a maximum elongation. You can't go further. Because if there is a component, meaning either it is still, didn't reach maximum elongation, or it reached and it is coming back already. Component of a spring must be zero. That is, velocity is perpendicular to the spring. This is your state 2. Now tell me one thing. How many equations did I write till now? I didn't write a single equation. But did you see how much thought process went into the equation? Now, if this was an exam, I will get this done in 10, 12 seconds. But this much should go in your head in the 10, 15 seconds. And this will take time. You will get it. You will get that kind of speed. But when you start solving, this is how you should think for every problem and start solving. Any doubts on this page? Now, once you got these jobs done, now the actually easy part. Now the concepts will come. Now the working and solving will come. I know initial state. I know final state. State 1, state 2. Conservation of linear momentum. L initial is equal to L final. Angular momentum is mr v perpendicular. So this is m L v sine theta. This is, let me call it E. Oh, already I used V. Yeah. Let's call this V dash. ML V sine theta. This will be M into L plus X into V dash. It's already perpendicular. So V dash will be LV sine theta by L plus X. This is the first one. Second thing, energy conservation. Energy in state 1 is equal to energy in state 2. Initial energy half mv square, only kinetic energy is there. Final energy half mv dash square. There, as expected, v dash is not zero. If v dash is zero, the angular momentum would be zero. But you said it is constant. And energy half kx square. This is your equation 2. Take v dash from here, substitute here. Simplify, you'll get x ka value. Actually, you get two roots. You got x1, x2, you get a quadratic. So that is elongation and compression. Because u said v is perpendicular, it happens 2 times. You can leave it here. Once you get the numbers, you can solve. But other steps clear, everyone? Again, how did I start? You said find maximum elongation. The moment I heard the word maximum elongation, I know it is conservations. You're getting it? This is what I'm saying. When you're solving questions, these are the things you need to learn. These things, no one will teach you this in any book. You can read 100 books, but you will never learn this kind of things. How do I know I should start like this? Isn't that the big thing in every exam, in every question? How do I know I should start like this? That way, when I hear the word maximum elongation, I know you're talking about a final state. And the only chapter you heard about final state is conservations. So there is no other chapter we did that. And when you say conservations, I remember 3 conservations: linear momentum, energy, and angular momentum. Then I said, okay, let's see now which one will work. I said linear momentum, it won't work because there's a fixed point. Then you say, and when the moment you hear the word fixed point, you should say displacement is zero, means work done is zero. Means energy is conserved, but linear momentum is gone. The spring force is passing through, so torque is zero. But with that information, still it is not over. I still need to have a discussion about this V dash, it is perpendicular. Now you have all the info. Now, if you actually see the mathematical parts, it's only 2 equations. Is this clear, everyone? Keep this in mind. Decent question, good one. And later on, we will make a statement, if a particle is not going in a circle and it is going in any random path, huh? For example, is this some random path, stretching, compressing, and weird? In 11th and 12th, we have only one way to solve: conservation of angular momentum and energy. There is no other technique that you can use to solve in 11th and 12th at least. So about that, we will talk in gravitation. You'll have, particles going in ellipse, particles going in parabola. You have different trajectories you have. We can't solve those things normally. The only technique we have is angular momentum. Next one. We got a disk here. Mass m, radius r. We have a bullet of mass m traveling with speed u. It hits the thing and gets stuck. Find omega final. Mass is not same, capital M and small m. So if you see the top view, this is fixed in the center hinge. Bullet is coming and getting stuck here. Now I can even say like this thing. There's a merry-go-round and a person goes and jumps on this thing and this thing starts rotating. Again, masses are not same. So you can clearly see here. This is an easy one. This is a standard model, like, this is a normal question in mains and bits. So the bullet goes and gets stuck here. And after getting stuck, the whole setup will rotate with omega. So torque about the hinge is 0. Be careful whenever you use the word stuck, meaning E0, right? You can't conserve energy. If the bullet is getting stuck, means it's a perfectly inelastic collision. Energy conservation is not valid, isn't it? E0. And there is a hinge. It is fixed in the center, means there's an external force. You can't conserve linear momentum. तो गया एक ही बचा angular momentum. So torque about hinge is 0. What is the initial angular momentum? The bullet is only coming MUR. What is the L final? L final, the bullet ka speed is also now. V bullet is R omega because it has got stuck. So this will be disk mr square by 2 omega plus bullet will be mass m, perpendicular distance r, speed will be r omega. This is for the bullet. This is for the disk. And then L initial is equal to L final. Equate them, you end up with omega is equal to mu by mr by 2 plus small m r. That's your answer. Clear? Easy. Moment of inertia of a disk is I omega. It's a rotating body, and bullet is a particle, so MVR perpendicular. Next one. Same thing. We can ask in another way. We have the disk, mass m, radius r. Now we have a person here, mass m. He jumps with his speed u. We did this in momentum. Man jumps with speed u related to the platform. I hope you remember that word. Means he's not actually jumping with you. With respect to the platform, he's jumping with you, but the platform is already moving with certain speed by the time he jumps. Find omega of the platform after he jumps. This is a fixed hinge. The disc can only rotate, it can't go front and back. So this and the previous one are kind of related. There the bullet is coming and getting stuck, here the man is jumping from it. Speed u related to the platform tangentially. He jumps tangentially. Right behind. Again, same story. So initially he is just standing there. The whole system is at rest. So initial angular momentum, 0. After this person jumps, this will go with omega. So this point where he jumped, right, that was actually going with r omega. So this person, when he jumped, if you look at his velocity, he was going forward with u and the legs were going back with r omega. Make sense? The person was actually going with u minus r omega. Hope that is clear. That is the meaning of u relative to the platform. So when he's about to jump, the platform is already going back. It is not like he will jump and then the platform will go. What is the final angular momentum? For the disk, I see OM omega plus k cap plus man will be mass m, perpendicular distance r, speed will be u minus r omega minus k cap. Be careful, directions are important. You are taking angular momentum from this point, the hinge. L initial is equal to L final. L initial is 0. This would be mr square by 2 omega plus minus mr into u minus r omega. Interestingly, you'll get the same answer as the before. You'll get mu mr by 2 plus m. This and the previous one will give you the same answers. Clear with this? So initially everything is at rest. So initial angular momentum is 0. So when the man jumps forward to compensate, the disk will go backward. Any doubts on this? Next one. Next one. These are like standard models. Some mains and bits main, these are like, they do come repeatedly types. The next one is even a better question. So let's say we got a disk. This is point A, this is point B. So AB is the diameter. And here we have a person, man of mass M. This is a disk, capital M and radius R. Now this man walks tangentially man of mass M walks along the circumference and reaches point B. Do you think when he's walking, the disk will be at rest? When he is walking, friction will be which way for the man? Forward. So the same friction will act backward on the disk. So that means the diagram will look like this. If you look at the top view, so initially A was here, B was here, man was here. When the man starts walking, A comes here, B comes here, man reaches B. So in reality, man didn't walk all the 180 degrees. That disk must have rotated some theta. The man actually walked pi minus theta. Is that making sense? So when he is walking, the disk is also coming towards him. That means he didn't cover 180 degrees. Find the angle rotated by disk. That is, I'm asking you find theta. Now, exam they won't give you this diagram to explain all that. That you need to figure it out. I hope you can see the similarities. It kind of looks like, man walking on a plank, find the displacement of the plank jaisa lag raha tha. Looks like that, but here angles are involved. How do we do this? Get this. This is a good one, right? This would go to even at an advanced level. It's a decent question. How would we proceed with this? Think, take a minute or two. Try, take a minute. Just get some water and come. Any ideas? Pi इंटीग्रेशन का जरूरत नहीं है. Let me show you. It's little. You should have an idea about this. Either you need a little, a lot of time to think, or you should have seen this before. Listen to the logic here. So this was our diagram. Now here, angular momentum of the system is zero because it's at rest. Now angular momentum of the system is nothing but I disk, omega of the disk, plus I man, plus omega into omega of the man. The total is zero. So this will be I disk. Omega of the man can be written as d theta, disk by dt, plus I man, d theta man by dt. If you send dt that side and you put it, you end up with I disk delta theta, disk plus I man, delta theta man. Now from here, if you see, moment inertia of the disk is mr square by 2. The theta of the disk, it is rotating that way, so it is theta k cap. Man ka moment of inertia is a particle, mr square, and its displacement is pi minus theta minus k cap. So if you just arrange this, you will get theta is equal to, actually, if I leave in terms of I disk and I man only, you will get a general result also. This would be I man into pi by I man plus I disk. That would be m pi by m by 2 plus m by 2. Mr square by 2, no, disk will cancel. So if you actually think about this, how it is looking like. The man walking on a plank problem, small m, capital M, length was L. There the distance moved of the plank was ml by m plus m. Here the angle rotated by the thing was I of the man. So mass is getting replaced by moment of inertia. I of the disk plus I of the man. Can you see it? It kind of looks like that. So it's actually a general result. You can use that if a question like this comes, saves you time. If the initial angular momentum was not zero, then it would be a mess. Then we have to send dt that side, and then we'll get LDT also. Could be solved. It'll be a little more lengthy. But this is the idea there. You should get the same result from integration also. If you say integration, I actually did the same thing, isn't it? When I integrated this, d theta became delta theta. Is this clear, everyone? There, Disca problems. Out of the three, this was a good one. So you have a problem like, bullet going and getting stuck, man jumping from the plank, and then man walking on the plank. Clear? Next one. Next one. So we have a solid cylinder. Mass m and radius r. This is going with v, going with omega. There's no slipping. As this is going, you got a step here. I'll just exaggerate this a bit. Whose height is r by 4. This point is a. And e is 0. Means when it collides, it will stick to the point. So this solid cylinder rolls and comes and hits the point A, and it rolls over the step. The solid cylinder hits the step and rotates about point A. Meaning diagram would look like this. Something like this. So this point got stuck here. So this thing will be like a hinge. The whole thing is rotating like this. And finally, I want it to climb the step. You're getting it? If I come too slow, what will happen? I will hit and I'll fall back, right? If I go too fast, what will happen? I will hit and bounce off. So there is a minimum velocity. So find V minimum so that it just climbs the step. Again, remember, I said it will get stuck at point S. So you can't conserve energy during collision. Is the whole scenario making sense, everyone? think of like this, when you're going on a cycle and if there's a small step, didn't you do something like this? You go, let's say if there's a small step, you go fast on a cycle and you just go over the bump, isn't it? But in real life, the cycle, right, he is not zero, so it'll kind of bouncy and it does all stuff. But if he is zero, this is what would happen. It would get stuck there and the whole system will rotate about it. See, I'll try to show you something. It's not exact, but yeah, it kind of works. This is from Avengers. I hope everyone remembers this scene. So they're fighting, they're killing everyone. We will ignore all this.
Loki's gonna keep this fight.
There. You know who is that guy? The Hulk.
So, this all seems horrible. Sorry.
No, we could.
We got him.
Banner, I'm bringing the party to you.
Now look at this thing. There. So that is our block or the cylinder which is coming with speed V.
I don't see how that's a party.
Hulk is our obstacle.
Banner. Now might be a really good time for you to get angry.
That's my secret, Cap. I'm always angry.
There. Can you see that thing? So that thing is coming with full speed V and this guy hits it and one stop. So you can see Hulk got stuck to that. And see what happens. Can you see how is the whole thing rotating? Can you see the whole thing is rotating about the obstacle? Samajh mein aa raha hai? Kind of like this. So you can see this is like some kind of a spherical thing. It's rotating about the Hulk. So Hulk is the obstacle and this cylinder is this object thing.
Hold on.
Yeah, this we don't have in the portion, so that's out of the portion. Shooting it down and killing it. There, can you observe now? Here we have Hulk here, and this is that alien monster coming up, and the alien monster hits the Hulk and climbs up. So if Hulk actually, or if that monster doesn't come with enough speed, right, it would have just, gone up like this and would have fallen down. It wouldn't have climbed completely. It wouldn't have toppled. Got this thing. These are problems of the physics teacher. When you go to the movie and you're watching, this is what you think. Oh shit, angular momentum is comes out here. How do we solve? Again, same thing. Can I conserve energy? No, because it is getting stuck. Can I conserve linear momentum? No, because you're hitting there is a force. Then there is only one thing left, angular momentum. So about which point? Now the question is come which point? So if you try to draw the free body diagram, so this is the thing just before collision. This is. So at this point, if you observe, you will observe there is a normal reaction, there is a friction, there is also an mg, but again mg is non-impulsive force, so we can ignore this. So during the time of collision, mg is non-impulsive, therefore we can ignore for that small time. So if you take this point, and so therefore you can say torque about A is almost zero. Therefore, angular momentum about A is constant. This is what I told you in the last class. The biggest problem in angular momentum, right? Most people think, oh, it is complex and all. No, most people don't know how to calculate angular momentum. That's what we spent last time. If you know how to calculate angular momentum, 70% of the question is there with you. So now you have to conserve angular momentum. How will your diagram look like? So initially this guy is coming with V and omega. And then you're still there, you're just about to collide. Now this whole setup is rotating with omega dash. So it behaves, A behaves like a hinge. It's pure rotation. So you have made a motion of a rolling motion into pure rotation. This is pure rotation about A. This is point. So initially it is rolling. So L initial is equal to L final. L initial will be angular momentum of center of mass plus angular momentum about center of mass. I taught you in the last class. How much is this distance here? Extend the vector, drop the perpendicular. So this will be 3r by 4. That would be mv 3r by 4 direction minus k cap plus ICM omega. It's a cylinder mr square by 2 omega minus k cap. Finally, it is purely rotating. So I about A into omega final or omega dash minus k cap. And since it is not slipping initially, V is equal to R omega. So if I substitute here, V is equal to R omega, that will be 3 by 4 plus half 5 mr square omega by 4. And this guy would be, it's a solid cylinder, mr square by 2 plus mr square by 2, 3 mr square by 2 omega dash. So we get omega dash is 5 omega by 6. Check. This is the angular velocity just after collision. So once you hit A, this is the omega dash. This will start rotating about this point. Now, after the collision is over, energy is conserved, isn't it? Once the collision is done, energy is conserved after collision. So during collision, you can't conserve energy. Because whatever deformation has to happen, that happened. So whatever energy lost and all that went into deformation, after that, whatever is there, now there is no more further deformation. Now we use conservation of energy after collision over. Now your steps will look like this. So initially the A was here. Finally, you climbed on the top. This was A. This was your center of mass. This height was R, and this was going with omega dash. When you have climbed completely, you just reached here. So omega final is 0 because it just reaches. You said V minimum. So all your rotational kinetic energy became potential energy. So half IA omega dash square plus mgr became mg 5r by 4. This is half IA is 3mr square by 2. Omega dash is 5 omega by 6 whole square. This would be mgr by 4. M will cancel. Omega will be how much? 4 will cancel. 6. 4 will cancel. How much is this? 3 r 25 omega square by 36. This is gm is gone, r is gone, 4 is gone. Omega will be 12g by 25r का root. That's your omega. This is equal to v by r omega, तो v भी आ जाएगा. Yeah, I can make g10 and simplify further, but there. Are the steps clear, everyone? So energy is conserved after collision. Angular momentum is conserved during collision. So there are two parts in a problem. After the collision is over, energy is conserved, but angular momentum is not conserved because mg is an external force now. Are the steps clear, everyone? It's a good one. Now this question, you can change the shape, you can change the height of the step. right? You can do multiple things, but this is the theme in these kind of questions. If E is not zero, it will be a mess. If E is not zero after collision, this ball will fly up Vy, it will have Vx, it will go like a parabola. A lot of nonsense can happen. So it becomes very difficult to solve. So generally you'll get E0. Any doubts on this? Anyone not convinced with anything here? Please ask. I definitely should try all the problems we're doing today. Should try in entire rotational mechanics, last class, angular momentum, and today's class. This is the most important one. People find this is the toughest one. All you need is little practice and understand. The most important thing is conservation of calculating angular momentum. Next one. Next one. Next one is another standard models. Important mains and bits may they do ask a lot. So let's do one simple one, then I'll ask you one more. I'm pretty sure everyone went for bowling, right? So when you go for bowling, do you observe what you do actually? You throw the ball onto that floor. You give only velocity. You don't give any omega, isn't it? When you throw the bowling ball, you throw with speed v, right? You don't rotate the ball. And then what will happen after some time? The ball will start rolling on its own. It will skid for some time and eventually it starts rolling. Right? So find v final and omega final. A solid sphere is thrown with speed v without omega. So it skids and then starts rolling after some time. Let's say friction is mu. Find v final and time when slipping stops. The step was of negligible and then you just take it as r, right? The total height will be mvr instead of 3r by r by 4. But in that case, you shouldn't take a solid sphere. You should take something like a cube or something. That would be better because if you take a negligible height, this thing will just cross over and go. Nothing will happen. Center of mass का height change नहीं हो रहा है ना? 7v by 5. Speed increased somehow. We have an energy pioneer. I'm proud of my class. You are the future. You're going to save the world from energy crisis. I always, tell these medical people that, the way we are consuming and stuff, we will destroy the earth in the next 70, 80 years. It will change my statement. We have people who can save the earth now. Listen, I'll show you one model. This is a good one. Then I'll give you one more. Now, there are two ways to do this. One is a lengthy way, find the force, acceleration, stuff and all, but there's a much faster way. Now, when you throw this ball onto the floor, now remember it is skidding. So if you actually try to see the forces, we have normal reaction, we have mg, and because you're skidding, you also have a friction maximum. Agreed? N and mg will cancel. Now, if you choose any point, on the floor, right, N and mg cancels, and F max passes through point A. Therefore, torque about A is 0. If you take any point on the ground, torque is zero. Doesn't matter. Make sense? If torque is zero, then angular momentum is conserved. Therefore, L about A is constant. Again, remember, energy is not conserved, linear momentum is not conserved, but angular momentum is conserved. Then you're done. So initial diagram, final diagram. So this was point A, this was point A. So initially you're only going with V, omega is zero. You're going with V final, you're going with omega final. L initial is equal to L final. Last class I taught you this, how to find angular momentum for a rolling body. Angular momentum of a rolling body is angular momentum of center of mass. So you treat the center of mass like a particle. Extend the vector, drop the perpendicular. That would be mv r. Directions are important, minus k cap. Omega is not there. This will be mv final r minus k cap plus ICOM omega final minus k cap. Since it is not slipping finally, v omega is r omega final. Minus sign goes off. MBR, MV final R. It's a solid sphere, so 2 by 5 MV final R. So we get V final is equal to 5V by 7. And you can clearly see here, F max is nothing but mu mg. So there'll be an acceleration backward. So if I calculate that, F max is equal to ma. So we get A is equal to mu g. Since I know V final, this can be written as nothing but U plus AT. So this will be 5E by 7 is equal to V minus mu g T. There we get time is equal to 2V by 7 mu g. Once you got the final velocity, time will come pretty fast because it is skidding. F is maximum and F is equal to ma. There's no other horizontal force. And it is constant. I know final velocity, I know initial velocity, I can get time. So conservation of angular momentum, we'll get the answer in like, what did you do actually? Just conserve angular momentum, one step. So the main thing is that when you're skidding, the friction on the floor will always pass through any point on the floor. So you can take any point on the floor, it works. Because end of the day, you're interested in perpendicular distance. Is this clear, everyone? Clear? Pretty important questions. These are repetitive. Again, when I say these are standard models, understand you are writing two mains, two bits, 4 exams that is. Then you have UGE exam, IIIT Hyderabad. Then you have Manipal, you have Vellore. You have almost 7 exams. Somewhere it will pop up. Advance is also there, but he can. Now, similar one, you guys try this. Let's say we have a disk, mass m, radius r. This you give velocity v, and this you give omega backward, which is 3v by r. Find v final and omega final. You know how to give velocity like this? If you take a carom ka coin, if you ever did this, take your coin, put it vertically, put your finger like this, and push it down. Kabhi kiya? If you press like this, what will happen? The coin will go forward and then will come back again. So when you're pushing like this, what you're doing, see, when you push like this, your friction, you're making it rotate this way, but this normal reaction is pushing it forward. You can try this with your carom ka coin. So when you don't know how to play properly, you do all this kind of nonsense. So I know better. Let's get this. Same thing as previous one, but I just increased it, I just gave an extra omega also. Idea is still the same. Torque about any point on the ground is zero. Answers. Nickel. When you saw the question, did you get a feeling omega is too high? And I know what you did. You messed up the sign. Signs are important. Let's see. Yeah, it will be negative. The thing actually comes back. So finally, I don't know how it is going, so don't worry, assume forward. Let the signs take care of it. Omega final. So take torque about any point. So torque about A is 0. Therefore, L about A is constant. So L initial is equal to L final. So L initial, angular momentum of center of mass, mvr minus k cap. Angular momentum about center of mass, ICOM omega mr square by 2 omega. That would be plus k cap. This would be mv final. So extend the vector A. So this is the perpendicular distance. mb final r minus k cap plus mr square by 2 omega final minus k cap. So if you have taken this minus, you'll be gone. You can't add them directly. Be careful with the signs. The omega and v, the rotational and the translation angular momentum subtracting in the initially. Now substitute the values here. So this would be minus mvr. Omega is 3v by r. So this is 3 mvr by 2. This would be v final is r omega final minus 3 mv final r by 2. So we get v final minus v by 3. It's actually going back. That's what I'm saying. You don't worry which way it is going. Science will take care of it. Check. Clear, everyone? These are one important problems. Any doubts on this? If they ask you time, the same idea. F is mu mg, you got a, v finally is equal to u plus 80, finish off, you'll get time from there. Anyone confused with this? Clear, na? Nikhil, Pratik, Vignajit, Devansh, Arya? Clear? Next one. This is another important models. Collision problems. Do you guys remember in linear momentum when I taught you collisions, what are the 2 steps you do? In collisions, head-on collisions or whatever, what are the 2 steps we do? Linear momentum, restitution. Bus. We draw the final diagram, V1, V2, and then we say linear momentum and restitution. Is there any other thing we do for collisions? Isn't it? That's what we do. So even here we do something similar, but we'll get one more additional thing. So top view, first we'll see one general one, then we'll see variations. M and L. Let's say we have a ball here. Traveling with speed u hits the end of this thing and restitution is E. So this is a rod placed on a smooth floor. This is the top view. Find the velocity of the rod, omega of the rod, velocity of the ball. After collision. I can also ask you, find the point on the rod whose velocity is 0 just after collision, basically IAR. Let's do the first part. Second, I'll show you anyway. Think. Take 2 minutes. Try to figure out what are the steps and all, and then I'll show you one. This we will do in general. Just write the equations. How many variables are there? V rod, omega rod, V ball. So 3 variables. I need 3 equations. Get me the equations. Or whatever you can think of. Ian, how do you think about this? First thing, it is clear. I'm asking you velocity after collision. Means we have to use conservations, right? Force and torque equations won't help. That is clear. So what is the first thing you have to do? Draw the final diagram. Like I keep saying, if you don't know how your final situation looks like, you won't be able to take a decision. And don't think it's only about physics. Tomorrow, when you get a job, you need to think, should I take a job in this company? How will my future look like? You need to visualize. If I do this startup, what are the problems that I'll face? You need to visualize. Every damn thing that you do in your life, you have to visualize. Itna kyun? If you plan a movie with your friends on a weekend, don't you plan and visualize? Are we will call that guy, we will call this person, that person. Then you'll say, yeah, but that person never comes. He is always late to the movie. You plan, right? Movie is at 12 o'clock. So what do you tell your friends? Are movie is at 11:30? Because this guy is always 10 minutes late. That guy also will actually look into the movie and he knows it's actually at 12. So that guy also plans. So you do visualize. You actually do this every day on a daily basis. Right? You broke something in the house. You start visualizing, what is mom going to say now? She's going to beat me. She's going to shout on me. How do I react? Can I put this blame on my sister? So you think all different possibilities. Right? So you do that every day. So top view, initially situation, this is how it looks. The rod was at rest. The ball M is coming with speed. This was before collision. After collision, let this go with V1. Let this rotate with omega. Let the ball go with V2. I don't know any one of them. Remember, this V1 is the center of mass of the rod. When you say translation, remember, you always talk about the center of mass. So V1 is velocity of center of mass of the rod. Perfect. So this is after collision. There you got your final diagram. Step 1. Since the external forces are 0, I can conserve linear momentum. So during collision, ball in the rod array system, F external is 0, momentum is constant. So initial momentum is mu, final momentum is m into v1 plus m into v2. Remember, Omega does not affect your linear momentum. Momentum of a system is mass into velocity of center of mass. Omega is useless. Rotational does not affect this thing. So this is your step 1. Step 2. When you write the formula E is equal to V2 minus V1 by U1 minus U2, you need to ask yourself, if the body is colliding here, what the hell is this V1 doing there, right? Tell me one thing, does this velocity has anything to do with this point of collision? So V2 and V1, these are actually velocities of points of collision. They're not center of mass velocities. These are velocities at the point where the collision occurs. Because when the ball is colliding in this corner, what is V1 ka velocity doing? It doesn't make sense only to take V1. These are velocities of points of collision. That means if I take this point velocity from the V1 plus L omega by 2 rotation, this is velocity profile. So now when you write the formula, E is equal to V2 ka place mein we have V2 minus V1 ka place mein we have V1 plus L omega by 2. That is a catch by U1. So this point ka velocity U1 is 0 and this is U2. So U1 minus U2. You can take any one as 1 and any one as 2. This is U. This is your equation to everyone. Quite an important one. This is the mistake people do. They take V2 minus V1. So this is the velocity of the bottommost point. Is this making sense, everyone? If you remember in head-on collisions, isn't this the 2 steps we do normally? Momentum and restitution. The only catch in restitution here is you should take the velocities of the points of collision. Any doubts on this? Have a look at this page. Step 3, since external forces are 0, that means torque is also 0. Now this is even better. Torque is 0 about any axis. If there are no external forces, then their torque is 0 about any axis. So step 3, torque about any axis is 0. Therefore, L bar about any axis is constant. So now it depends on you which point to choose. I'll show you 2 points. I'll show you the center of mass and I'll show you one more point which I like. That actually saves you time. But technically, you can take any point you want. You can take random anywhere point, answer still works. So first, let's take the center of mass. Again, I'll draw the final diagram. So this was mass M, this was at rest. This was mass M, this guy is going with V1, this guy is going with omega. And here the ball is coming with U. The ball is going with V2. Okay. This is the center of mass. L initial 0. This is for the rod plus the ball, which is mu, perpendicular distance L by 2. Extend the velocity, drop the perpendicular. Direction plus k cap. Directions are important because it rotates like this, anti-clockwise. L final. L final rod will be, you're talking about center of mass. So this is for the ball. You will have 0. So transition will be 0 plus ICOM omega k cap. This is 0 since V1 passes through center of mass. If your velocity passes through center of mass, then there's no angular momentum about this. Plus ball will be mv2 L by 2. That is also plus k cap. There, L initial is equal to L final. So you end up with mu L by 2 is equal to, the rod is ml square by 12 omega plus mv2 L by 2. This is your equation 3. 3 equations, 3 unknowns, so you'll get the answer. Check out this. But there is much better point. Any doubts on this page? There's nothing wrong with this. You take the 3 equations and solve, you'll get the answer. It is lengthy because I gave all variables. But there is one more better point. Step 3. If you take torque about the point of collision, since you said any point is there, we'll take angular momentum about point of collision. You will see why this is more convenient. Is also constant. So your diagram initial, your diagram final. This was mass and this was at rest. So ball is going with you. This was point A. After collision, ball is going with V2. This is point A. This is going with V1. This is going with omega. We are conserving about A. L initial, ball is passing through this 0. Rod is also 0. Make sense? L final, ball is 0. Getting it? So ball, that is for ball. So velocity, right? U is passing through A. V2 is also passing through A. So the only thing left is rod. So for the rod about point A is what? I taught you how to calculate this. MV1 L by 2. Directions will change minus K cap plus ICOM omega plus K cap. There. So this also has to be 0. Everything is 0. So then this term also has to be 0. So L initial is equal to L final. So this is 0. We get MV1 L by 2 minus sine plus ML square by 12 omega. We will get V1 is equal to omega L by 6. Can you see? The third equation looks pretty neat actually. And be careful, this is not a unique equation. Huh? This is also 3, this is also 3. If you actually take this momentum equation and substitute here, you will get this equation back. So you don't get any unique equations. If you conserve angular momentum about A or center of mass, it is the same thing. L about A and L about center of mass won't give you unique equations. Once you conserve angular momentum about any point, done. You didn't create any new equations. Are not unique. So use any one, don't use both of them. So if you take linear momentum equation, substitute here now, you will get that V is equal to omega L by 6. The reason I like this thing is, look at this equation. You have small m, we have omega, we have V2, capital M. There are too many things there. This thing looks pretty neat. On top of it, this thing will help you to solve the second part of the question pretty easily. But is this thing clear, everyone? So I prefer to take angular momentum about point of collision, but you can take any point. So whenever I solve, I'll always take about point of collision. Generally. I'll show you a case where taking about center mass is also better sometimes. The second part of the question, you are asking find the point on the rod whose velocity is 0 after collision. So this guy is going with V1, this guy is going with omega. So consider a point here at a distance x. So this will have velocity V1 and this will have x omega. So you're saying V1 minus x omega must be 0. But I know V1 is omega L by 6. X is equal to L by 6. That is your IAR. That point has a 0 velocity at that instant. Make sense? So if I ask you find the point whose velocity is 0, I can skip the step 1 and step 2 now. I can skip step 1, I can skip step 2. I can just use step 3 ka angular momentum about collision and I can get the answer in one step. That's the reason I like this third one. So if you ask me, this is also step 3 only. It's not a unique one. Is this clear, everyone? So whenever you have collisions with rods, this is how you do. Step 1, draw the final diagram. Step 2, linear momentum. Step 3, restitution. Restitution, be careful. Velocities must be at the points of collision. Step 3, angular momentum conservation about any point. I prefer center of mass or point of collision. You can actually take any point. It works. And after collision, these are the velocities. If you want the point to have zero velocity, so v1 minus x omega must be zero. Any doubts on the equations, please ask. All clear with the steps? Take a break. Come back by 7:07. We'll continue from here. We'll do more models on this ball and this Rodka collisions. Any doubts so far? Okay, come back in 10 minutes. Yeah. Find V rod, omega of the rod, and V of the ball after collision. Same thing. I just gave you some, numbers like, M and 2M, so now they'll cancel out. You'll get some values now. Get it? Same thing. Step 1, draw the final diagram. Step 2, linear momentum. Step 3, restitution. Step 4, angular moment. Get this. I'll give 3 minutes. Get this. Get this. Any answers? Let's see the equations. I hope everyone has written your equations. Check your equations. If you got the equations right, then it's just a matter of solving. So step 1, the final diagram. So after collision, let this guy go with V1. Let this go with V2. Let this rotate with omega. So this point of collision, the speed will be V2 plus L by 4 omega. So I'm going to take angular momentum at that point. Step 2, linear momentum. P initial is equal to P final. Initial momentum mu, final momentum mv1 plus 2mv2. U is equal to v1 plus 2v2. Remember, linear momentum is unaffected by omega. The body rotate doesn't matter. Angular momentum of the system is linear momentum of the system is mass into velocity center of mass. Next thing, quotient restitution. E is equal to v2 minus v1. So v2 ka place mein we have v2 plus L omega by 4 minus v1, the ball ka velocity, by ball ka velocity u minus 0. This is given as half. So V2 plus L omega by 4 minus V1 is U by 2. This is your equation 2. You could have taken one into reverse, that is fine, but you should get something similar. That's your equation 2. Next thing, I will take angular momentum about A is constant. L initial is equal to L final. Initially ball is 0, rod is 0. Finally ball is 0, rod will be angular momentum of center of mass mv2 L by 4 minus k cap plus ICM omega ml square by 12 omega plus k cap. This will give you V2 is equal to omega L by 3. This is your equation 3. Check. There is a 2m, but luckily the 2m actually gets cancelled, so I'm still safe. The other thing I like about the third part, because the small m doesn't come into the picture, it works out. It will cancel out m. Please check your equations. See where did you mess up, or did I mess up something? So if you got this, I think job's done. Physics part is over. Final diagram, linear momentum, restitution, and angular momentum. Now it is just a matter of solving. Check your steps. Anyone not clear with this? Solve. I'll give you a minute more. Let's see the equations. So U is V1 plus 2 V2. This was equation 1. V2 plus L omega by 4 minus V1 is U by 2. That was equation 2. And V2 is omega L by 3. This was equation 3. Perfect. So let's get V1 from here, which is U minus 2 V2. Let's put it in this and put V2 in this. So eliminate everything. This will be omega L by 3 plus omega L by 4 minus U minus 2 V2, but V2 is again omega L by 3. Or actually, I can keep everything in terms of V2 only. V2 plus omega L is 3 V2. So this is 3 V2 by 4 minus V1 is minus U plus 2 V2 is U by 2. 3v2 plus 3v2 by 4, 4, 3, 12 plus 3, 15 v2 by 4 is 3u by 2. So v2 will be 2u by 5. There, once I get this, I can get v1, I can get omega, I'll get everything. Check. Solving is an easy part. Any doubts on the equations? Clear? This page is clear, then this is fine. Clear? Let's see one more. Let's see one more. We have a rod here, 4m length L. We have a ball here, mass m, going with speed. If hits the top end, E is equal to 0. It sticks. Top view again. The ball sticks to the rod after collision. Find velocity of center of mass of rod plus ball. Find omega of the rod or the system after collision. So because it is sticking, they will go together. Find velocity of center of mass of the rod. Be careful. A and C are different questions. Center mass of the rod is different from center mass of the system. Let's get this. Try. 2 minutes more. Let's see. Step 1, the final diagram. The game is still the same, nothing changes. But luckily, actually, number of steps will decrease because E is 0 and it will stick, right? So there's no need to write the restitution equation. Now you need to ask yourself, like, where is the center of the system actually? It's not the center of the rod. If this is M, this is 4M. If this is the center, let's call it O. Where is the center of mass? So this is M, this is 4M. If I take this as 0, 0, this is 0, L by 2. The center of mass is somewhere here, which will be M into L by 2 by total mass, L by 10. So the center of mass of the system is somewhere here. This green one is the center of mass of ball plus rod. This is at a distance of L by 10. So after sticking, which point goes in a straight line? The center of mass of the system, right? So this guy is actually going with a velocity v center of mass. So when you conserve momentum, initial momentum P initial is equal to P final. So initial momentum is mu. The final momentum is m plus 4m into v center of mass of the system. V center of mass is u by 5. Actually, even if you calculate V center mass before collision, this was the same thing. How do you calculate V center of mass? M1 V1 plus M2 V2 by M1 plus M2. The V center of mass before collision would be M into U by M plus 4M. It is the same thing. Obviously, it should be the same because collision is an internal force. It is not affecting the center of mass. So before collision, after collision, doesn't matter. The center of mass is going with U by 5. But the center of mass is this point, not the center of the rod. And this whole setup is rotating with omega. Any doubts still here? So first part we got. Now we need to find the omega. Now we can take torque about any point. It works, but I will choose my center of mass. How much is that distance then? If that is L by 10, L by 2 minus L by 10 multiply 5, 4L by 10, 2L by 5. So this distance will be 2L by 5. Here also you can take torque about the thing, but it is fine. So angular momentum about center of mass of the system is constant. So L initial is equal to L final. So L initial only the ball is going, which is M U 2L by 5 direction minus K cap. Finally, angular momentum of the system, which is angular momentum of center of mass, which is 0, because velocity of center of mass is passing through VCOM, passes through center of mass. Plus ICOM omega. But be careful, this ICOM is not one single thing, it is a rod plus the ball. So I center of mass will be I ball plus I rod. The ball will be M into 2L by 5 whole square plus the rod will be 4ml square by 12 plus parallaxis theorem. 4m L by 10 whole square. You have to take from the center of the rod, no? That would be your ICOM. Please check the steps. And once you got this, you will get omega from here. So basically omega will be 2MUL by 5 I center of mass. There, I'll get omega from here. We can substitute there. I will leave the working to you. What else did I ask you? Velocity of center of mass of the rod. So there I know omega, I know velocity of center of mass, so I think I'm done. So basically this point here is going in a straight line with U by 5. And the whole setup is rotating with omega. This is the center of the rod, so this is going with U by 5. And this will be L by 10 omega because this distance is L by 10. So velocity of the center of the rod is U by 5 minus omega L by 10. Please look at the steps here. So you draw the final diagram. We conserve momentum. Restitution we don't need to write because when you say E is 0 means it is sticking. The moment you say it got stuck means you already used E ka value. Third is angular momentum. There, the 4 steps are still there. So the main catch is this. When they ask you center of mass of the system, be careful. It is not the rod or the ball. It's the center of mass of the cumulator. So it got actually shifted. It's L by 10 above the center. Any doubts on this? Please ask. You should definitely try all these problems on your own. And if you're doing HCV, right, I think question 57 to 64 or something, there is a bunch of 7 to 8 problems. All are based on similar models. You should definitely try that. Any doubts on this? Let's see one more. We got a rod here, ML. We got a ball here, small m, going with speed u. E is equal to half. This is the top view. The ball stops after collision. So then find the ratio of m by small m. Ball stops after the collision. Similar, just something a little more different information. This will be a good integer question. Poroja, you're right. Let's see. Step 1, draw your final diagram. This would be nice because it stopped. You actually have so after the collision, this guy came to rest. This guy went with V and rotated with omega. Initial momentum is final momentum, so mu is capital MV. One equation. Distribution E is equal to, now you need to take the velocity of this point here, which is V plus L omega by 2, which is V plus L omega by 2 minus velocity of the ball, which is at rest, by velocity of the ball U minus 0. This is off. So we have V is L omega by 2 is equal to U by 2. This is equation 2. Next thing, you can write about any point. I will choose this point for angular momentum. L about A is constant. L initial is equal to L final. Initially ball is 0, rod is 0, initially 0. L final ball is 0, rod would be mvl by 2 minus k cap plus ml square by 12 omega plus k cap, which is 0. So we get v is equal to omega l by 6. Perfect. So take equation 3 and put it in equation 2. If you put equation 3 in equation 2, we get omega L by 6 plus omega L by 2. 2 omega L by 3 is U by 2. So U is equal to 4 omega L by 3. Put this in equation 1. So M into U will be 4 omega L by 3 and capital V is omega L by 6. If we do M by M, 3 to 8 is to 1. Check. Clear, everyone? There, I didn't change anything. Final diagram, linear momentum, restitution, angular momentum, done. The only thing here is, in this case, the final velocity of the ball is given indirectly. So just substitute there and you'll get the answer. Any doubts on this? Next one. And if you see, right, this is how we do every time. Like, whenever there's a problem, we have a process. That's what I keep telling you. When you know your process, exam may write, this thing won't happen, like, how to start. That should not be a problem. At least in an exam like mains or bits, right, when you see a question, the moment you see the question, first 10, 15 seconds, 10 seconds, you should know, in this question, I should do this, I should do this, I should do this. And then maybe 1.5 minutes can go for actually doing all that stuff. The biggest problem, students have is when you go to the exam, they think, I will think in the exam, then I will try to solve in the exam, you're gone. You're getting it? Then that will slow you down. You won't be able to solve 25 questions. Advance may fir bhi, it is fine because you have only 18 questions and you have more time. So, and in that 18 also, if you do even 12, 13 questions properly, you'll still get a good score. But mains and bits, you will have a problem. Let's see one more. We have a hinge here, we have a rod here. So this is mass ml. There's a rod hinge at the top. We have a ball of mass m traveling with speed u, restitution is e. It goes and hits the rod somewhere here at a distance x. And we observe, so find x if hinge reaction is 0 during the collision. So when the ball is colliding with this rod, the hinge reaction is not there. Neglect gravity. So quite an interesting thing. This thing, right, is actually called point of percussion. There's a name for this. Meaning, think about this. Let's say if you're playing cricket, if you're having your bat, right? If this is your bat, and that means if the person who is holding the bat, right? So this is the hinge, right? Hinge is the point where the batsman is, holding the bat. Think about it. The ball is coming with a speed of 140, 130 kilometers per hour, and you're hitting it back, and you're playing this for 100, 200 balls. It puts a lot of stress on your hands, isn't it? But from this question, if you see, that means there is one particular spot on the bat. If you can hit the ball at that spot on the bat, the hinge reaction is 0. That means the batsman will not feel any much, will feel very less stress on his hands, isn't it? So in cricket now, there's a thing like this. I don't know whether in commentary now they say this, but when I was in school, the commentary used to be like this. The ball has hit the bat on the sweet spot and the ball is flying and gone for the 6. Okay. So they use the word called sweet spot. Ever heard that term? There is something called a sweet spot on the bat. That sweet spot is actually point of percussion. If the batsman hits the ball at that spot, the reaction on his hands is minimal. So he can swing the bat with full force and his hands will be still fine. And generally, if the ball actually hits at that spot, right, it really goes very far. So in cricket, right, we call this thing point of percussion, sweet spot. Now, this much they will say leave in the exam, but let's discuss a little more. I'll give you an idea there. Now, tell me one thing. During the collision, if this point is trying velocity forward, then the hinge will try to pull you back, isn't it? If this point is trying to go backward, the hinge will push you forward, isn't it? Now you tell me the hinge is not pushing you, pulling you. Matlab kya? That point is not even trying to move, right? Meaning during collision, if somehow this point has zero velocity, then there'll be no hinge reaction. Is that making sense? If you catch at a point where there is a zero velocity, right, you're neither pulling nor pushing, isn't it? So the whole question is that they're indirectly saying find x when, if the hinge reaction, the point on the hinge is zero velocity. So during collision, the velocity of the point on the rod connected to the hinge has zero velocity. So the point which you connected to the hinge, if it has a zero velocity, that means the translation rotation got cancelled. Then there's no need for any hinge reaction. There is no need for the hinge to pull you only. There, that is the whole point of the question. So find x so that the topmost point of the rod has zero velocity. Since the hinge reaction is zero, means you can ignore the hinge actually. You can remove the hinge and solve the problem normally because anyway it is zero. Try. Now this is what I'm saying. Questions will be framed like this. So since the hinge reaction is zero, remove the hinge. And remember I told you, if you just want the velocity, you can just go with step 3. You don't need to do momentum and restitution. So first thing, draw the final diagram. So you are going with m with speed u, you are hitting somewhere here. This point is a, this distance is x. So after collision, the speed will be something else. Let's call it v2. The rod ka velocity will be v1. This is trying to rotate with omega this way. This distance will be x minus L by 2. This is point A. Now, if you look at the velocity profile also, you're saying this is going with V1 and this is omega. So the topmost point is going V1 forward and going back with L omega by 2. So V1 minus L omega by 2 must be 0. This comes from the condition the velocity is 0, equation 1. Then angular momentum about A is constant. L initial is equal to L final. Initial is 0 because ball is passing through this. Finally, also ball is passing through this. This is mv1 x minus L by 2 minus k cap plus rod will be ml square by 12 omega plus k cap. Take that v1 and substitute here. M gets cancelled. This will be L omega by 2 x minus L by 2 is L square omega by 12. L omega cancels. This thing goes off. X minus L by 2 is equal to L by 6. X is equal to 2L by 3. Pretty interesting answer. You know why? Did you observe one thing? It didn't depend on mass of the rod, mass of the ball. It didn't even depend on restitution. It didn't depend on E. It didn't depend on mass of the thing. So that means in cricket, if you see, it does not depend on mass of the bat. It does not depend on mass of the ball. It does not depend on speed of the ball. It does not depend on the restitution of the ball. That means there is always one particular spot on the bat. If you can hit there, the batsman's hands will be safe. You play with the tennis ball, you play with a cork ball, you play with anything, it doesn't matter. You can actually calculate that point on the bat. You can mark it and you can make the batsman practice, hitting the ball at that spot. Now, as a coach, that's what you will do. As a player, you might not know this much, but the coach will tell you. Always try to make sure the ball, gets contact at this spot. Clear with this? It's a good one. Can you see, how the questions are? If you see all the questions, the theme is something similar. Final diagram, momentum, restitution, angular momentum. You have nothing more than that. Sometimes we use one of them, sometimes we use all of them. So that variation you will get with practice. Now, if you can understand this much, this is one important model of problems in angular momentum, the rods and collisions and stuff. Clear, everyone? This is one type. Next thing is the angular impulse. Let's say we have a solid sphere. Mass m and radius r. Someone gave an impulse here, j, at a height h. What is an impulse? Maybe you're playing snookers or something, you just hit it. You're getting it, you're just punched it there. This is an easy one. So, but you should know how to get this thing. Find V and omega. After impulse, find h if the body starts pure rolling. In case you forgot, I'll just brief you. Impulse j is nothing but change in linear momentum, which is mv final minus mv initial. And then we have change in angular momentum, delta L bar is nothing but r bar cross j bar, or you can take r perpendicular into j. This is your angular impulse, change in angular momentum. This is the relation between angular impulse and angular momentum. Try. I'll give you a minute. Then I'll show you one and I'll give you one more. So these are straightforward questions. So just after collision, right, the impulse j, the force is so high, you can ignore all these non-impulsive forces. नहीं पूर्वजा. Right, Vihan. So see. So initially it is there. Let the final velocity be v and let the final velocity be omega. You are giving an impulse j here at a height h. So first step, j is equal to change in momentum, which is m into v. एक ही step that done. V is equal to j by m. Second step, change in angular momentum is, so angular momentum about center of mass. You have to decide. So this will be r perpendicular from center of mass into j, which is h into j. This is nothing but I into omega. What is I? 2 by 5 mr square. Omega is equal to 5hj by 2 mr square. Bus direct steps though. If you want pure rolling, V is equal to r omega. So j by m is equal to 5hj by 2 mr. H is equal to 2r by 5. If you remember, we did a question like this before. Where should I apply the force so that friction is zero? Do you remember? That was this. Clear? Let's see one more. So that's it. Whenever there's an impulse J is given, this is what you do. J is changing M into V center of mass. R perpendicular into J from center of mass will give you the angular momentum from center of mass omega. So let's say we have a table here. We have a rod here, mass m, length l. Consider this point as origin, this point as 0, L, and this is point A. Now what you did, you gave an impulse J here from the center of mass at a height of L by 3. What do you mean by impulse again? You're kicking it, you're getting it, you're just kicking it. Now when you kick this, what do you think will happen? The rod will start going like this now. You're getting it? This, the rod will not be, the rod will then become like this. And then the rod will become like this. So the rod will start rotating. So this is point A, this is point A, this is point A. So the A would actually go like this. Gravity is there. Find coordinates of A as function of time t. The floor is smooth and all. So it's like you keep maybe a water bottle or a pen or something on the edge of the table and you just hit it. Now this thing will spin and go, right? If you look at this path of A, this A is actually going like this. A is not going normally. It is, rod is rotating and translating. Find the coordinates of point A. First of all, just after collision, what are the velocities? So just after collision, let the velocity be v and let this be omega. We are giving an impulse j here at a distance of L by 3. So j into L by 3. So first j is equal to mv. There I got the velocity. Next thing, angular momentum about center of mass will be perpendicular distance L by 3 into j is ICOM omega. L by 3j is equal to ml square by 12 omega. Omega is equal to 4j by ml. There I got omega and v. So once we got this, then it kind of becomes a kinematics question. So this was your rod. Now tell me one thing, during this entire motion, there's one particle which is just going in a parabolic path, center of mass, isn't it? The center of mass of the rod will go in a projectile motion. Isn't that the whole point of center of mass? Goes in a projectile. So this height is L by 2. This velocity is v. So after some time, your center of mass will reach here, where the horizontal distance will be v into t, and the vertical distance will be half gt square. It has fallen, so the coordinates will be this: vt, comma L by 2 minus half gt square. Does it make sense? It has traveled horizontally, distance vt, and vertically it has traveled half gt square down, but your initial height is L by 2. These are the coordinates of the center of mass. And what happened to your rod? Your rod has become like this at an angle. I'm exaggerating the figure like this, like an angle theta. What is theta? Theta is omega into time. This is your point A. Now you can ask, how do you know theta is like that? I don't know. Theta will take care of it. It is obtuse angle, it will take care. This would be the distance. So this would be L by 2 sine theta and L by 2 cos theta. Do you guys remember this question where we did? Momentum. First question though. Didn't we do something similar here? Projectile motion of the center of mass and the rod ka rotation circular motion. And this is where I told you, this is how the chapter starts karke. Center of mass was the starting point. So there you're done. So x coordinate of A will be x center of mass plus that extra distance L by 2 sine theta, which is Vt plus L by 2 sine theta, which is omega t. Similarly, y coordinate of A will be y center of mass plus L by 2 minus half gt square. L by 2 cos theta, which is L by 2 minus half gt square plus L by 2 cos omega t. There, done. Check. Other steps clear, everyone? There. With that, we are done with rotation. We have done 85 questions. Right? I think after kinematics, this was the biggest one, I guess. So do resolve 85 questions, especially what we did today in last class. These are important. So resolve all these 85 questions and start solving your material. In case you have not started, do finish off. If you're doing DC Pandey or HCV, do finish off. At least take time till next Friday and wrap it up. Okay. So next class when we catch up, we'll be starting off with heat and thermodynamics. So any doubts in today's class? Anything else you can stay back and ask, also feel free to leave. So take care, stay safe. Exam ka deadline is till Friday evening, 11 o'clock. So make sure to give.